At 4:55 in the morning Pacific time on September 15, 2017, a signal traveling 83 minutes at the speed of light from a point 1.2 billion kilometers away reached the Deep Space Network Antenna Complex in Canberra, Australia. And then nothing. No more signal. No more data. No more Cassini. The spacecraft that had been humanity's eyes at Saturn for 13 years, that had orbited the ringed planet 293 times, that had flown past 127 of Saturn's moons and revealed liquid oceans and methane seas and hydrothermal vents in places nobody expected to find them, that spacecraft had just become part of Saturn itself, vaporized in the planet's upper atmosphere at 70,000 miles per hour. The engineers in mission control at NASA's Jet Propulsion Laboratory in Pasadena, California, were crying. Some of them had spent their entire careers on this mission. The room went quiet when the signal ended, and then, slowly, as the grief of the ending settled, something else took over, because in the final 22 orbits of the grand finale, in the last plunge through the gap between the rings and the cloud tops, Cassini had transmitted data that nobody at NASA fully understood yet. Data that described a planet behaving in ways that violated the models scientists had built over decades. Data that, 7 years later, is still generating new discoveries. Data whose deepest secrets, as of 2026, remain unexplained. To understand what made Cassini's final months so extraordinary, you need to understand what the grand finale actually was, and why it produced science unlike anything the mission had generated before. Cassini arrived at Saturn in July 2004. For 13 years, it operated in orbits that kept it safely distant from the planet's cloud tops and from the innermost ring, orbits designed for longevity and for mapping the broad structure of the Saturnian system. In those 13 years, it revolutionized planetary science. It discovered a global subsurface ocean inside the tiny moon. Enceladus, complete with hydrothermal vents on the ocean floor and water vapor plumes erupting through cracks in the ice shell that carried hydrogen, silica nanoparticles, and complex organic molecules into space. It discovered liquid methane seas on Titan, the only stable liquid surface other than Earth's oceans in the entire solar system. It documented seasonal changes on Titan, photographed the hexagonal polar storm on Saturn's north pole that spans an area larger than two Earths, and detected auroras and lightning storms and the mysterious spoke features in the B-ring that appear and disappear on timescales that nobody can fully explain. These were the discoveries of the main mission, the first 13 years. And they were enough to establish Cassini as one of the greatest scientific spacecraft in history before the grand finale ever began. The grand finale was what happened when the mission team realized the spacecraft was almost out of fuel. Rather than simply allowing it to drift indefinitely and risk accidentally contaminating Enceladus or Titan, both of which might harbor life and neither of which could ever be explored again if contaminated by earthly microbes stowed away on a spacecraft, the team made a decision to end the mission deliberately and scientifically. They used Titan's gravity in a final flyby on April 22, 2017, to reshape Cassini's trajectory in a way that sent it into a series of 22 daring orbits, each one diving through the 2,000-kilometer gap between Saturn's innermost ring and the planet's upper atmosphere. This region had never been explored before. No spacecraft had ever passed through that gap. Scientists expected it to be relatively empty, a clean, featureless void between the inner D-ring and the cloud tops. What Cassini found there was the opposite of empty. The gap was full of surprises. Every orbit through it produced data that rewrote a piece of what scientists thought they knew about Saturn. And the data that came out of that gap is still producing published papers in 2026, still revising models, still raising questions that have no complete answers. The first and most immediate discovery from the grand finale was ring rain, and the scale of it was nothing like anyone expected. Scientists had known since the 1980s, from indirect evidence, that Saturn's rings were slowly losing material to the planet. Charged particles in the rings travel along magnetic field lines and fall into the upper atmosphere, delivering a trickle of water and dust to the planet below. This slow erosion had been estimated at somewhere between 432 and 2,880 kilograms of material per second, based on ground-based observations of Saturn's ionosphere. When Cassini flew directly through the gap and sampled the material raining down from the innermost ring in real time, the measurements came back between 4,800 and 45,000 kilograms per second, between 2 and 100 times higher than the indirect estimates. That is an enormous range. The uncertainty in the measurement is enormous because the flow is extremely variable. But even the lower end of the range is more than 3 times the previous upper estimate. This material was not just water. It was a complex mixture. Molecular hydrogen, water ice, carbon compounds including butane, propane, and more complex organic molecules, silicates, and nanometer-sized dust grains. The rings were not just raining water onto Saturn. They were raining chemistry, organic chemistry, onto the planet's upper atmosphere at a rate that nobody had imagined. And the implications for the long-term survival of the ring system are significant. If the rings are losing mass at this rate, they could be far younger and shorter, lived than classical models suggested. Some calculations from the grand finale data suggest the rings might have formed as recently as 100 million years ago, and when dinosaurs still walked the Earth, and could disappear within another 100 to 300 million years. The iconic rings of Saturn that have captivated astronomers for 4 centuries may be a temporary feature of the solar system, not a permanent one, and it took Cassini's final orbits to reveal that. The second discovery from the grand finale is one that has generated more scientific confusion and more ongoing research than almost any other result from the mission. Cassini's magnetometer, built and operated by a team at Imperial College London, made the most precise measurements of Saturn's magnetic field in the history of planetary science, getting as close as 2,550 kilometers above the defined atmospheric surface. What those measurements revealed was a magnetic field aligned with Saturn's spin axis to within less than 0.001 degrees, less than 1/100th of a degree. That is essentially perfect alignment, and perfect alignment is, according to every model of how planetary magnetic fields are generated, theoretically impossible. The magnetic field of every planet with a functioning internal dynamo, Earth, Jupiter, Uranus, Neptune, is tilted with respect to its rotation axis. Earth's magnetic poles are offset from its geographic poles by about 11 degrees. Jupiter's magnetic axis is tilted roughly 10 degrees from its spin axis. The tilt is not a quirk, it is a requirement. The mathematical theory of how rotating, electrically conducting fluids generate magnetic fields, dynamo theory, predicts that a perfectly axisymmetric magnetic field, perfectly aligned with the spin axis, cannot sustain itself. A field that has no tilt produces no differential rotation between different latitudes of the conducting fluid, which is what drives the current loops that maintain the field. A perfectly aligned field should decay. And yet, Saturn has one. Professor Michel Doherty, the lead scientist on Cassini's magnetometer at Imperial College London, said in 2018 that the results looked increasingly like science would have to rethink the ways different kinds of planets can form magnetic fields. 8 years later, that rethinking is still in progress. As of April 2026, a new analysis of 6 years of Cassini's magnetometer data published in Nature Communications by researchers from Lancaster University found that Saturn's magnetic field is lopsided in a way that Cassini's data revealed only recently, shifted asymmetrically in a manner that may be caused by the influence of Enceladus's own magnetic interactions with the planet. The field that appeared perfectly aligned in the initial grand finale measurements has turned out, on closer examination over longer data sets, to be more complex and more broken than that initial result suggested. But the fundamental mystery, how Saturn maintains a near-perfectly axisymmetric field at all, remains open. The third major revelation from the grand finale involves Saturn's interior, and specifically the question of how deep the planet's surface winds extend. Saturn's visible cloud patterns, the bands, the jets, the hexagonal polar vortex, are driven by winds that blow at hundreds of kilometers per hour. But the clouds are just the surface expression of those winds, and a critical question for understanding Saturn's internal structure is how deep the winds reach. Are they a shallow atmospheric phenomenon confined to the outermost few hundred kilometers, driven by solar heating? Or do they extend deep into the planet's interior, connecting the visible cloud layer to the denser metallic hydrogen below? Cassini's gravity measurements during the grand finale, taken with exquisite precision as the spacecraft flew through the gap where the planet's gravity field is strongest and most detailed, revealed a gravity field with complex asymmetric north-south variations. When the scientists modeled these variations, they found that the winds extend to a depth of approximately 9,000 kilometers below the visible cloud tops, about 1/7 of Saturn's radius, deep into the planet's intermediate molecular hydrogen layer. That is not a shallow atmospheric phenomenon. That is a planet-scale flow that reaches into the deep interior. The pattern of the gravity anomalies was described by the research team as remarkably complex, more structured and asymmetric than expected, implying an internal differentiation between the planet's north and south that is still not fully characterized. Then there is the mystery of the gap itself, the region between the innermost ring and the atmosphere, and what Cassini found living there. The space between the D ring and Saturn's cloud tops contains a radiation belt, a region of energetically trapped charged particles analogous to Earth's Van Allen belts. Scientists knew the Van Allen belts existed because Earth's magnetic field traps particles there. Saturn was known to have its own radiation belts in the main magnetosphere, outside the rings. What nobody expected was a separate, newly discovered radiation belt specifically in the gap between the rings and the atmosphere, in a region where the rings themselves should be absorbing energetic particles and preventing their accumulation. Instead, the gap had its own distinct population of trapped particles with energies and intensities that required the gap to act as a particle accelerator in some local process that the grand finale measurements could document but not fully explain. A completely unexpected radiation environment in a region specifically where the model said particles should be absorbed. This new belt was one of the 11 simultaneous discoveries published in Science and Geophysical Research Letters on October 5, 2018, and it remains one of the least understood. The discovery that has generated the most follow-up research since 2017, and the one most directly connected to new findings in 2026, is the puzzle of Saturn's apparent rotation. Cassini detected in 2004 that Saturn's radio emissions, which pulse in a way that should be synchronized with the planet's internal rotation, were measuring a slightly different rotation period than what Voyager had measured in 1980. A planet cannot actually change its rotation period. The interior of a gas giant rotates at a fixed rate determined by its angular momentum, and nothing that happens in the atmosphere or magnetosphere can change that rate on human timescales. What Cassini was measuring had to be something else masquerading as a rotation signal. In 2021, Professor Tom Stallard of Northumbria University and colleagues showed that the apparent change in rotation rate was being driven by winds in Saturn's upper atmosphere, producing electrical currents that modulated the auroral radio emissions, making it look like the planet was spinning at different rates, when in fact it was the atmospheric winds that were changing. But that explanation still left a critical question unanswered. What was driving those atmospheric winds in the first place? In March 2026, 9 years after Cassini's death, the James Webb Space Telescope pointed its near-infrared spectrograph at Saturn's northern polar region for a full Saturnian day on November 29, 2024, and produced the first detailed temperature and density maps of Saturn's auroral ionosphere at 10 times the spatial resolution that Cassini-era instruments could achieve. What JWST found was a self-sustaining feedback loop. Saturn's aurora heats the upper atmosphere. That heating drives winds. Those winds generate electrical currents. Those currents sustain the aurora. The aurora then heats the atmosphere again. A planetary heat engine, powered by Saturn's own magnetic field and the solar wind interaction, continuously cycling and maintaining itself. Professor Stallard described it as changing how we think about planetary atmospheres more generally, because if Saturn's atmospheric dynamics can drive currents out into the surrounding space environment, the same feedback loops may operate at Jupiter, Uranus, and Neptune, reshaping how scientists have been interpreting decades of observational data from all 4 outer planets. But perhaps the most profound legacy of Cassini's entire mission, including the grand finale, is not Saturn itself. It is what the spacecraft revealed about Enceladus, the small icy moon that sits inside Saturn's E-ring, and whose secrets Cassini uncovered piece by piece across 13 years of flybys. And the data from those flybys, like the grand finale data, has not finished speaking. In June 2023, a team led by planetary scientist Frank Postberg at Freie Universität Berlin published a study in Nature using Cassini's cosmic dust analyzer data and confirmed something that changed the entire scientific community's assessment of Enceladus as a potential home for life. They found phosphorus, specifically sodium phosphates, locked inside salt-rich ice grains ejected from Enceladus's south polar plumes. Phosphorus is the least abundant of the 6 elements considered essential for life on Earth: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. It is the backbone of DNA, the structural component of cell membranes, and the core of ADP, the molecule that every living cell uses to transfer energy. For years, it had been conspicuously absent from the list of confirmed Enceladus plume ingredients. Every other essential element had been detected. Phosphorus had not. The 2023 discovery filled the final gap. The ocean of Enceladus, as sampled by Cassini's instrument during flybys of the E-ring, contains all 6 elements essential for life as we know it, at concentrations of phosphorus at least 100 times higher than in Earth's oceans. Then, in December 2023, a NASA study analyzing the same Cassini plume data found strong confirmation of hydrogen cyanide, a molecule that, despite its reputation as a deadly poison, is considered by origin of life chemists to be one of the most important precursor compounds for the emergence of biology. Hydrogen cyanide is a starting material for the synthesis of amino acids, nucleotides, and other molecular building blocks that life depends on. Finding it in the ocean of Enceladus, ejected into space by the same geological process that revealed the subsurface ocean's existence, moved the needle again on whether Enceladus's ocean is not just habitable in principle, but actively engaged in the kind of chemistry that could lead to life. The same study also found evidence of an energy source in the ocean, a powerful chemical disequilibrium between oxidants and reductants, similar to the chemical energy gradient that drives hydrothermal vent ecosystems on Earth's ocean floor, that could power biological processes even in the permanent darkness beneath Enceladus's ice shell. Then in November 2025, a paper published in Nature Astronomy using reanalyzed Cassini data found complex organic molecules in the fresh ice grains of Enceladus's plumes that had never been documented before. The molecules included esters, ethers, and compounds containing both oxygen and nitrogen, molecular fragments that, on Earth, are involved in the chemistry associated with, even larger, biologically critical molecules including lipids and amino acid precursors. The research team, led by scientists at the Freie Universität Berlin, who had also confirmed the phosphorus discovery, described the chemical inventory as a clear sign that complex chemical reactions are taking place within Enceladus's underground ocean, reactions that could be part of chains leading to even more complex, potentially biologically relevant molecules. ESA's science team described the discovery as further strengthening the case for a dedicated mission to orbit and land on Enceladus. None of this data was collected after Cassini died. All of it came from Cassini's instruments, from flybys that happened years before the grand finale, analyzed and reanalyzed by scientists developing new techniques and applying new understanding to the same raw numbers that have been sitting in databases since 2017. Cassini is still discovering things. The spacecraft burned up in Saturn's atmosphere nearly 9 years ago, and it is still discovering things. What is still not explained, what remains genuinely open science in 2026, despite everything Cassini recorded and everything JWST has since added, is the internal structure that allows Saturn's magnetic field to maintain its near-perfect axial alignment. The leading hypothesis, developed by researchers at Harvard and elsewhere in the years since the grand finale, involves a stable, stably stratified layer of helium and neon rain deep inside Saturn, a layer that sits between the hydrogen-dominated outer layers and the metallic hydrogen interior that acts as a filter for the magnetic field, smoothing out the tilted field generated by the deeper dynamo into the aligned field observed at the surface. In this model, the field is actually tilted deep inside the planet, yet the stable layer damps and filters the non-axis symmetric components before they can reach the surface, leaving only the perfectly aligned component to emerge. It is an elegant hypothesis. It is also completely unverified, because no instrument can see inside Saturn. Neither Cassini nor any telescope in existence can measure the interior magnetic field below the outer atmosphere. The gravity measurements from the grand finale constrain the interior mass distribution, but the connection between mass distribution and the dynamics of the deep dynamo region requires assumptions that the data cannot directly validate. The ring spokes, dark, ghostly features that appear and disappear on the B ring, extending radially outward from Saturn and rotating in synchrony with the planet's magnetic field, rather than with the orbital speed of the ring particles, were first seen by Voyager in the 1980s and remained unexplained for decades. Cassini observed them extensively, confirmed they are composed of tiny electrostatically levitated dust grains lifted above the ring plane by electromagnetic forces, and documented their seasonal appearance. Strongest when Saturn is near equinox, weakest near solstice. But the complete picture of how the ring's electric environment couples to the planet's magnetic field to create and maintain the spokes is still not fully understood. After years in which the spokes disappeared from visibility, the Hubble Space Telescope documented their reappearance in Saturn's ring in 2021 and 2022, as the planet approached its next equinox. The James Webb Space Telescope is now monitoring them. The data Cassini collected on spokes is actively being combined with current telescope observations to build models that still do not fully work. Cassini project scientist Linda Spilker, who spent more than 3 decades of her career on the mission, said in the immediate aftermath of the grand finale that many mysteries remain as we put together pieces of the puzzle. And that results from the final orbits turned out to be more interesting than they could have imagined. That was in 2017. In 2026, the puzzle is larger than it was when she said it. Every piece of new analysis, the lopsided magnetic field from April 2026, the aurora feedback loop from March 2026, the complex organic chemistry raining from the rings, the deep winds reaching 9,000 kilometers below the cloud tops, the impossible near perfectly aligned magnetic axis, the unexpected radiation belt in the gap, the phosphorus in Enceladus, the hydrogen cyanide, the complex esters and ethers, the ring spokes that no model fully explains. Each new piece fits somewhere in the picture, but the picture it reveals is not simpler than what scientists expected when Cassini arrived at Saturn in 2004. It is more complicated, more structured, more alive with processes that interact in ways that current planetary science cannot fully model. Saturn is not a planet that has been understood and filed away. It is a planet that keeps answering questions with more questions, using a spacecraft that burned up in its atmosphere 9 years ago, and whose data, as Cassini's magnetometer team at Imperial College London predicted in 2018, continues to yield new discoveries that none of them expected. The signal from Canberra went silent at 4:55 a.m. on September 15, 2017. But what Cassini transmitted in its final seconds, and in the 22 daring orbits that preceded them, is still speaking loudly in the language of published papers and unanswered questions to every planetary scientist on Earth. And the most extraordinary possibility of all, that an ocean world inside our own solar system may right now contain the chemistry of life, revealed entirely by a spacecraft we burned in a planet's atmosphere to protect that possibility, is the legacy that Cassini's data is still building, one reanalysis at a time.